Hello, statistics lovers, and welcome to another section of Math 215. This one is section 3.2, which deals with measures of variation, which basically is talking about how spread out the data are. Like, are they clumped right together, or are they spread out all over the place? So in section 3.1, we learned about measures of center. Right, we talked about the mean, the median, the mode, weighted mean, trimmed mean. All of those are measures of center. A measure of center alone, however, can be misleading. So, for example, two countries with the same median family income are very different as one has extremes of wealth and poverty, and the other has little variation among families. A drug manufactured with the correct mean concentration of active ingredients is dangerous as some batches are much too high and others are much too low. In these cases, we would be interested in the spread or variability of incomes and drug potencies as well as their centers. So these examples show it's not enough just to know the measure of center, because if you have inconsistencies and too much variability, it can be dangerous in those cases. So you got an example here for coaching basketball. I don't know if you guys have ever coached basketball before. I will tell you one thing though. This is something you may or may not know. But I found out that nowadays pretty much all kids play soccer. I don't know if you know that yet. But when you're a parent, most likely your kids will play soccer. It just seems to be the way it goes. I know you're thinking, I'm never going to have kids. I know. I used to think that too. But when you do have kids, here's a little something for you. You're going to want to write this one down. This will save you later on. When you drop your kid off for soccer practice on the very first day, if it sounds like maybe you think you heard somebody say something about need an assistant soccer coach, whatever you do not make eye contact at that point. If you look up to kind of say, what did you just say? If you look up like that, guess what you're going to be? You're going to be the assistant soccer coach. I found out the hard way. And even if you say something like, I can't do that, I've never played soccer, they're going to say, it's okay, we have videos to teach you. Okay, so just saying, be careful out there. But in this example, we're not coaching soccer, we're coaching basketball. So suppose you're preparing your team to play a basketball game. You have the list of the heights of the players who will be starting for two teams. And you're going to be playing one of these teams, but you don't know which one. The heights are listed below. So this is all we've got. We don't know much about these players other than we've got the starting 5 heights. So just so we can get some feel for what this is. So 68 inches. Remember, there's 12 inches in a foot. So 5 times 12 is 60. So this player is 5'8". And over here, 71 inches. This player is 5'11". So if you look at this team 1, everybody's pretty much the same height, right? There's 5'8". So this is going to be 5'10", 5'10", 5'11", 5'11". Not a lot of variation here. Now team 2, however, seems to be all over the place. They've got this player, it's 5'2". And then you've got this player is 6'6". This player is 6'8". So even if you don't know much about basketball, if you're a coach, you know that you're going to have to be able to prepare for some tall players, right? So with this, we've got these 2 team heights. Let's go ahead and just take a minute and find the mean. Find the mean of team 1 and find the mean of team 2. Okay, so to find the mean, of course, we add them all up, divide by how many there are. And you should, if you do this, you should find out this is about 70 inches, is 70 inches for the mean. And same thing here, 70 inches for the mean. So if all we knew was, let's say all we know is this, the average player on this team is 70 inches. In other words, 5'10". And the average player here is also 5'10". But these two teams look a lot different as far as height goes, right? These players are all about the same height. These players are all over the place, right? And there's two that are really tall. So we're going to find another metric here. We want to have another measurement to work with. So it says one number, which is the mean, isn't enough to describe the data set. We need a measure of how spread out the data are. And we've got a couple ways to do this. Before we do that, who was thinking, yeah, I do like the sound of that? Huh? You guys on board yet? Data R? Or you still on team data is? Run out of time here. Gotta make the jump. Data R. Okay. Again, it doesn't matter, but data R. So the range is the difference between the largest and smallest values of a data set. So do you remember on one of the homework problems, they said something about what are the range of the data using the midpoints, and we looked at a histogram. They were just using everyday language. Like in everyday language, you say something like, well, the temperatures in June tend to range between 70 and 98 degrees or something like that, right? Everyday language. Now we're going to change it. When we see range from now on in our class, when you see this word range, they're referring to a technical description right here, which is the difference between the largest and smallest values of a data set. So you take the largest number in the data set, subtract the smallest number in the data set, and you're going to get a number. So I'm going to write this in red because remember, red means danger. Range is a number. Range is a number. It's not 7 to 25. It's a number, right? So to find team 1 range, we just look. Difference between the largest and smallest values, 71 minus 68 gives us 3. And we can put the units on there. Typically you do in our class, unless they say otherwise you don't have to, but typically you do put the range on here. And then team 2 range, 80 take away 62 is a lot bigger range, right? 18 inches. So again, I'll put the units on here too. So the range, the nice thing about the range is it's easy to find. You can teach this to everybody, right? If you run an assembly line and you have some sort of quality control, this is a really easy measure to teach someone. So it's easy to find, but it has a problem. So think about if you had an outlier. If there's an outlier, the range is going to use it, right? It's going to take the largest and subtract the smallest. If either one of these are outliers, you could get a number that's not really that meaningful. So the advantage is it's easy to use. The disadvantage is it's not as useful. So we're going to look at 2 ways of talking about measures of variation. They're both pretty common, but the one that is like the go-to method is this other one, standard deviation. This is the one we need to know about. This is the one everybody uses. It's not as simple to find, that's the problem. But it's a measure of the spread or distribution of data around the mean. So you're basically measuring how these data points compare to the mean, or how these data points compare to the mean. That's what the standard deviation does. Okay, so just to make it really clear again, range is a number. So don't say team 1 range 68 to 71. That's going to be wrong, right? We're talking about this mathematical concept of range. We want the difference between the largest and the smallest. So we don't want everyday language for the range anymore. So before we look at the formula for standard deviation, I want to give you some intuition about what it is. So to develop the intuition for standard deviation, we'll look at team one first. Look at team one. If you look at the heights of these players, they're all fairly similar. So if you were to say, if I were to randomly grab one of these numbers, just randomly select one of these numbers, how far would I expect it to be from the mean of all the numbers? Right? If I randomly pick one of these, how far would I expect it to be from 70 inches? Well, it's going to be pretty close, right? Because none of them are all that far away. Like if you pick this number, it's 2 inches away from 70. This one's 0 inches away, and 1 inch away from 70, 1 inch away from 70. So the standard deviation is essentially that. It's not quite that, but it's close. So let's think of it this way. What if you're going to just get the difference between this data point and the mean, and then this data point and the mean? So let's say you go down the list, you're like, okay, 68 take away 70, it's -2. 70 take away 70 is 0. And then again, 70 take away 70 is 0. So you're writing all these deviations to here. 71 take away 70 is 1. And then this 71 take away 70 is 1 again. You're like, hey, let's find the average of these numbers. Well, when you add up these numbers, if you're going to find the mean, you add them up, you get 0, right? Because this -2 cancels with these. So if you want to find the average difference, it's going to be 0, which doesn't make any sense. It's not helpful because these are not really averaging 0 away from 70. It's just as far as distance goes, because you got the negative. So we don't want the negative. So then you could say, well, let's take the absolute value, and that would clear that up. We just use absolute values. We get rid of the -2. And then we could talk about the average deviation, the average absolute deviation from the mean, right? And that would work. The problem is we're going to be needing to use calculus here, and calculus cannot handle absolute values. If you've taken calculus, you'll know that the absolute value function is not differentiable at the peak, at 0. So we can't handle absolute values, so instead what we do to make these numbers be positive, so remember the difference, if we set up some sort of formula, we're going to go 68 take away 70, you get a -2. We have to do these negatives, so what we do instead is we square these. That makes it positive, and then later we take the square root. So what we're left with is really close to the idea of, if I pick one of these numbers randomly, how far would I expect it to be away from the mean of all the numbers? It's real close to that, but it's not quite that, because the formula for the standard deviation squares the numbers, then squares these differences, adds them all up, and takes the square root. And that's not the same as squaring them, then immediately taking the square root, because we're adding them first. So you'll see it in the formula. We're going to do a couple of them by hand so you can see how the formula works. In reality, everybody uses software for the standard deviation, because if you have a lot of numbers, it's kind of a nightmare to do by hand. But the intuition we need when you see standard deviation, this is important, this is what we need, standard deviation. Think of it like this. If I were to select one of these numbers from the set, how far would I expect it to be from the mean of all the numbers? That's essentially what the standard deviation is. It gives us a measure of the spread or distribution of data around the mean. So looking at Team 1 and Team 2, isn't it true that Team 1 should have a small standard deviation compared to Team 2? Because look at Team 2, 62, this is 8 inches away from here. 5 inches away, 5 inches away, 8 inches away, 10 inches away. So if I randomly pick one of these numbers and ask myself how far should I expect it to be from 70, much farther than picking one of these, right? These are all close, relatively close to 70 compared to these. So when we figure out the standard deviation, this one should be smaller. So in general, if you have a small standard deviation for a data set, it means that the values tend to be close to the mean. So they tend to not be spread out very much. They tend to be close to the mean. If you have a large standard deviation, it means that the numbers tend to not be close to the mean. So they typically will be more spread out. So we have some formulas here. I know what you're thinking. Thinking those are some good looking formulas, and you are correct. These are one version of these. This is the ones that we'll use. You don't have to know this, but this formula right here, this sample standard deviation, this is called the defining formula. And this one is too. Both of these are called defining formulas. You don't need to know that, but the history of it is there's a defining formula and a computation formula. So in the bad old days, when you had to do standard deviation by hand, although standard deviation is defined this way, it's not as easy to use this formula if you're doing a bunch of data points by hand. So the book mentions something called the computation formula, which when you look at it, it looks like it's even more impressive looking than this. It's a crazy looking formula, if you're not used to mathematical formulas. So I'll just mention this, we don't need to know it, but the book also has what's called the computation formula. Okay, so this formula used to be an important formula. It's not so much anymore because now we have graphing calculators. So the reality is people tend to just do standard deviation by hand when you're learning it. It's just so you understand how it works. But once you learn it, you don't do it by hand. So when we didn't have graphing calculators, you still had to do it by hand, and this computation formula is a time saver compared to this formula. Okay, so in a regular class, I always have a quiz or a test where we had to do standard deviation by hand. So in an online format, we won't be able to. So we'll still do a couple of them in the lecture here by hand because I want you to see how it works. I want you to try a couple just so you see how it works, and then just realize that we'll use the calculator for the computations. So looking at this is a standard deviation from a sample. This is standard deviation from a population, and they have different formulas, right? So you can kind of see what we talked about built in here. So remember this capital sigma. Remember what that means? Sum. So we're going to take the sum of x minus x bar. Well, x, that's the individual data point. Each individual data point in your sample, we're going to subtract the mean of all the data, right? All the data in the sample. X bar is the mean of the sample data. Here's where that square comes in. We're going to square it because we can't deal with negatives, right? We don't want the negatives to cancel with the positives and make it seem like there's smaller variation than there is. So we square it, and then we divide by n minus 1. So it's kind of like taking the average deviation, but it's not quite the average, n minus 1. Well, the reason for that is when we are trying to find the sample standard deviation, it's usually because what we really want is the population standard deviation. So we're going to use this for a sample. And this is, in theory, more accurate to divide by n minus 1 because when you find your standard deviation, which remember shows you how the data are spread out, if you use a sample to do that, typically, if there's outliers in the whole population, you won't find them in your sample. So when you divide this by n minus 1, it makes this a little bigger and it makes it more accurate. It tends to be more accurate. Where the population standard deviation, if we actually have all the data, we just divide by n. We take the average of all these differences, right? So we divide by n, we take the square root. Here we divide by n minus 1, which makes this a little bigger because in theory we would probably, or in reality we would probably miss some of the outliers in our sample. Okay, so that's just something you don't really need to know that, but it's one thing I remember when I first saw this, I always thought, why would we divide by n minus 1 and not n? And then that's what I found out. That's why. So just a quick recall here. Remember X bar? That's a sample mean, right? The mean of the sample, n minus 1. Little n is the sample size, right? How many data points there are in the sample. And then look at the different symbols we have. Little s means standard deviation of a sample, just like X bar means mean of a sample. Then you've got sigma. This is small sigma, right? There's capital sigma, small sigma. When you see sigma in math, science, statistics, it represents the population standard deviation. So both of these are standard deviations, just this is for the population, this is for the sample, and they have different formulas, right? For the reasons we discussed here, it's n minus 1 here. So mu, that's population mean, right? It's population mean, and what's capital N? Population size, right? Okay, so we got sample standard deviation, population standard deviation, and we'll use this formula and do a couple of these by hand just so you can get used to it. So let's do that right now. It says find the sample standard deviation for team 1. Okay, so team 1, I'm going to write down team 1 again, what their heights are. So I just write it up here. So we've got team 1, and we had 68, 70, 70, 71, 71, and we know the mean is 70, right? We know the mean is 70. So we are going to use the sample standard deviation with these data points just to get used to doing this. So we'll do these by hand, and then we'll also do them on the calculator. So find the sample standard deviation. That's for team 1. Okay, so look at, we're going to use this formula, right? So little s equals the sum. So we take x minus x bar. Well, here's x bar. X bar is the mean. The mean of this sample is 70, right? The mean is 70. So we go right down the line, x. Each one of these individual data points is x. So first I'm going to pick 68. I go 68, take away 70, right? And then square it. So I'm going to get 68 minus 70 squared, right? That's this. Sum is, so I need to add, right? So I go plus. Okay, now we go to the next data point. Because remember, technically there's a little I equals 1 to n, and this is like x sub I, but we can just read it this way. It's a little easier. So now I go to the next data point, which is 70. So I go 70 minus the mean, which is 70. So you get plus 70, take away 70 squared, summation. So I automatically put a plus. And then we go to the next one, the next x. So we did 68, we did 70, now we have another 70. So you go 70 minus 70 squared plus, because it's a sum, we just keep on going. The next one is a 71. So put a 71 minus 70 plus, because it's a sum. And then finally we go to our last x, our last data point, which is this 71 right here. 71 minus the mean, which is 70 squared. And then the formula says divide the sum of all this, divide that by n minus 1. N is the sample size. The sample size here is 5. So divide by 5 minus 1. And then to make it super awesome, we want to throw a square root on there. You guys know you feel better if we at least do a square root problem, right? Okay, so here's what we've got. So I'm going to clean this up a little bit. So that equals 68 minus 70 is negative 2. I'm going to make a little mistake here, because I want to see, get you guys ready for this. 5 minus 1 is 4. Okay, now here's something that happens all the time. I want you to think of the difference between these two questions. When you ask your calculator to do this question, your calculator is going to use the order of operations. PEMDAS, right? Please excuse my dear Aunt Sally. When you do the order of operations, do exponents come first or subtraction? And it's going to interpret a negative as a subtraction. Exponents first. So this really means square this 2 first, square the 2 first, and then deal with a negative. So if we do this, we're going to get negative 4. Now, if you look at the formula for standard deviation, we can never get a negative. If you look it up here, whatever this is, we square it. Every time we put something here, we square it. So we are always going to get positive numbers. So because of that, remember, we don't want negative 2. We don't want the opposite of 2 squared. We want negative 2 squared. When you ask your calculator this, it's saying, okay, take two of these things, line them up and multiply them together, right? That's really what it means. That's a 2 there. This means take 2 of these, line them up and multiply them together, and negative times negative is positive, right? So we get a 4. So just be careful when you do this by hand. What you can do is just ignore the negative, because we know when we square these, they're all going to be positive. So if this is negative 2, you can just put 2 and square that. It's not going to be a big deal because we're not going to do a lot of these by hand. But anyway, what would happen here is we would get equals 4 plus 0 plus 0 plus 1 plus 1 all over 4. Which gives us 6 over 4. You take the square root of 6 over 4, and you will get roughly 1.22 inches. Okay, so that team 1 has a standard deviation of about 1.22 inches. So think about what that means. 1.22 inches essentially means this. If I randomly choose one of these, on average, I'm going to be about 1.22 inches away from the mean. Now, remember, technically, it's a tiny bit different than that, but that's a good intuition to have. That's everything we need. Just think, if I randomly choose one of these numbers, how far would I expect it to be from 70 on average? About 1.22 inches. Seems pretty close, right? That's 2 inches away, 0, 0, 1, and 1. So the standard deviation is a measure of spread. So I'm going to just write this one down. So this one, we know the mean, and now we know that the standard deviation is about 1.22 inches. Okay, and you can round that where you want to. Remember, we don't cover significant figures in here, so you can round where you want to. Just use judgment. You know, it's probably not going to be that helpful just to say 1 inch, right? A couple decimal places are probably better. So what you should do now is try this one. Try exercise 2. Try it on your own first, and then come back and let's see if we get the same thing. Okay, so here I've written team 2 over here, their heights. And so let's find the standard deviation. So little s. So again, using that formula, we are going to take the sum of all these differences. So we have x minus x bar. The first x is 62. Now we know the mean is still 70, right? We found the mean is 70. So we're going to go 62 minus 70 and square that. We're going to add 65 minus 70, and we go right down the list, right? So then we add another 65 minus 70, square that. 78 minus 70 and 80 minus 70. All over n minus 1. N again is the sample size. The sample size here is 5. There are 5 data points. So you go n minus 1. And then we take the square root of all of that. So that gives us negative 8. Remember, be careful. If I write it like this and I plug that in the calculator, it's going to tell me negative 64. And we know that we're going to get a positive number here because we're squaring it. So remember that really what we want is this. Then plus negative 5 squared plus negative 5 squared plus 8 squared plus 10 squared all over 4. And that gives us 64 plus 25 plus 25 plus 64 plus 100 all over 4. And that will give us about, let's see, we get 278 over 4. Take the square root of that and we get about 8.34 inches. So that is a much larger standard deviation than we had for team 1. So let's go back up here where we had team 1 and team 2. So the standard deviation here is 8.34 inches. So we went from 1.22 inches here to 8.34 inches here. So again, the intuition we need is this. If I were to randomly choose a number from this stack of numbers, from this sample of numbers, so I randomly pick one, on average, how far would I expect it to be away from the mean? 8.34 inches. Remember, technically, it's not exactly true, but that's the intuition we need for standard deviation. The intuition we need is choose one of these. Just pick one randomly. How far should I expect it to be away from 70 inches? About 8.34 inches, right? That's standard deviation. So I'll often later on this semester refer back to team 1 and team 2. And this is what I'm referring to. Team 1, everybody's pretty much the same, have a small standard deviation. Team 2, spread out all over the place, a larger standard deviation. Okay, so let's go back down here and look at this weird team 3. This is a weird team. Any question about what the mean is here? 70 inches, right? This is going to be 70 inches for sure. The standard deviation, what should it be? If I pick one of these, on average, how far will it be away from 70? It'll be 0 away, right? And that's the standard deviation of this is 0. So the smallest standard deviation we can have is 0. That just means there's no variation. Remember, standard deviation is a measure of variation, measure of spread about the mean. Both of those phrases work for it, but it's basically saying if I pick one of these, how far away should I expect them to be from the average? 0. There's no deviation at all, so that's kind of the extreme case. If all the numbers are the same, the standard deviation is exactly 0, and then it goes up from there. So to verify these Team 2 statistics using the TI 8384, so remember what you have to do first. You have to hit the stat button. Remember, hit the stat button to put the data into a list. And then once it's there, we have to run one variable stat. So remember, it's the stat button. Go over to calculate. And then the one variable stats is what we want. So we go to stat, then go to edit, and there are already numbers in there, so I go up and hit clear, enter, and then put the data in for team 2. So we've got 62, 65, enter, 65, enter, 78, enter, 80, enter. So the data are all in there. And now we go to stat again, right? Stat. Go over to calculate. And then we want one variable statistic. So we hit enter. And again, there's a couple versions of software. Some will just go right to it, and others go to this list. So just go through, make sure frequency list is empty, then go to calculate. And here's what we've got. So notice it says x bar equals 70, that's the mean. And then the next two we can ignore, the sum of x squared. Those are for if you want to do certain calculations by hand. Those are things that are used a lot. So they will sum all the values and sum all the squares, because there's certain calculations that you can break into parts and do by hand, but we're not going to do any of that. So the next thing to notice is, see, we've got an s there, s sub x. We've got this s sub x right here, and then also a sigma x. So here's what we have to know. We've seen there are different formulas for the sample standard deviation and the population standard deviation. So the calculator doesn't know if these data are from a sample or from a population. So it's going to compute both of them. It doesn't matter with the mean. Remember, if you have the sample mean or the population mean, the formulas are the same. So it'd be redundant to put x bar equals 70, mu equals 70. So they just put x bar equals 70. So standard deviation is different though, because these use a different formula. Remember, the little s is going to divide by n minus 1. This one isn't. So we have to know, do the data come from a sample or standard deviation? And that's something we'll work with this semester. But the calculator doesn't know. It only knows there's 5 numbers. It has no idea whether it's from a sample or a population. So you'll always get 2 values for standard deviation. Just remember, S, that's the sample standard deviation. Sigma, that's population standard deviation. And then we can go down. So it shows n equals 5. You can go down here, get the minimum, quartile, which we'll talk about later, the median, and the high. Okay, so it got the same thing that we did for sample standard deviation, so that is good. A couple things to note here. The population variance, this is just the population standard deviation squared, and the sample variance is just the sample standard deviation squared. So we can actually just ignore questions about variance in the homework. So we can just ignore it. So when you square the standard deviation, you also have to square the units. So when we know that the standard deviation for team 2 is 8.34 inches, that gives us information that's useful. It means that on average, the data points are about 8.34 inches away from the mean, right? But if you find the variance, you square that. When you square 8.34 inches, you get 69.5 square inches, which is not really useful. So the variance is just exactly the standard deviation squared. But normally you come with a variance and you take the square root of it to get the standard deviation. So when you have a set of data, you're going to typically want to know the standard deviation, not necessarily the variance. So in the homework, sometimes it'll say find the mean, find the standard deviation, find the variance, ignore the find the variance. It's easy to find, just whatever your standard deviation is, square it. But I'm not going to ask you about the variance, so just ignore it. So there are a couple other things in this section we need to know about, though. So one of them is the coefficient of variation. So let me just introduce this, and then we'll talk about it a little bit here. So since the standard deviation depends on the unit of measurement, it's difficult to use this to compare measurements from different populations. So in other words, if you are comparing a standard deviation with a set from, let's say, the age of GRCC students, well, that standard deviation is going to be in years. And if you want to somehow compare that to a standard deviation from a set involving like rainfall in Grand Rapids, which could be in centimeters or something like that, they're completely different units. So it would be hard to really make sense out of that comparison. So because of that, we have what's called a coefficient of variation, which expresses the standard deviation as a percentage of the mean. And you can see it right here. It's just expressed just like that. The coefficient of variation is the standard deviation divided by the mean times 100%. So this times 100% just puts it into a percentage. And this is the way our book always does it. You'll also see coefficient of variation expressed as a decimal. And it's the same thing, they're just not doing this last part here. So the coefficient of variation gives the percentage that the standard deviation is of the mean. And you notice there's two formulas here. They're essentially the same formula, but this one is for a sample, this one's for a population. All right, so you have little s sample standard deviation over x bar sample mean, or sigma population standard deviation over mu population mean. So to see how this works, we'll try one of these. But when we do this, you'll notice that the coefficient of variation has no unit of measurement. And then the question is why? Well, the y is basically, we can say that the units will cancel. And to see why, let's figure out team 2's coefficient of variation. So it's going to be little s, right, standard deviation 8.34 inches, divided by x bar, which was 70 inches, and then we multiply that by 100%. So when you were in algebra class, you would have learned that variables cancel. Like if there's an x here and an x here, they cancel. But you would have also learned probably that units also cancel. So that inch cancels with that inch. So that when we get done here, we figure out this decimal multiplied by 100%, but there'll be no units. So we'll get what's said to be a dimensionless number. Also remember, some people, coefficient of variation is just expressed like this, 0.119. But we are going to always use it always as a percentage, so we need this last step. Right, that's the way our book does it. So we're going to get 11.9%, which percentage in my way of thinking is better because it really tells you what you just found. We found out that for team 2, the standard deviation is 11.9% of the mean, right? So think if we had, let's say we had some data where the standard deviation was 50 or was 35 and the mean is 70. So that'd be 50%, right? So then the standard deviation would be 50% of the mean. So you really are finding, when it's a percentage, you're basically saying, okay, the standard deviation here is about 12% of the mean. So we'll always use percentages. Not everybody uses them. In coefficient of variation, when you get out of this class, for most of you, it won't really come up too much. But if you're in finance, you'll see it. In finance, the coefficient of variation allows investors to determine how much volatility or risk is assumed in comparison to the amount of return expected from investments. So in finance, you'll see it. And you'll even notice that the lower the ratio of standard deviation to mean return, the better the risk-return trade-off. So some of you will see this, many of you won't. But if you go into finance, you'll see coefficient of variation. And it's just like we talked about, it allows us to compare the variability of two different populations. And it's really just a measure of the spread of data relative to the mean of the data, right? The spread of the data relative to the mean of the data, because it's basically telling us the percentage the spread of the data is to the mean. So that is coefficient of variation. And I know what you're thinking. Every time we talk about something new, I know you're going to be saying, Kurt, I sure would like to try one of those. So here we got one for you. Exercise 5. Suppose we have sample data with a mean of 18, standard deviation of 3. They want us to compute the coefficient of variation. Remember, this is going to be a percentage, right? It's always going to be a percentage for us. So the formula is S divided by X bar times 100%. So that is going to be 3 over 18 times 100%. And I'm going to write this a few ways and have you guys tell me which ones are good and not good. Of course, you'll be voting from home, so I won't be able to hear you, but I'm just going to assume you're going to get it right. Let's do one more tricky one. Okay, so as you know, in this book or in this class, we don't cover significant figures or significant digits, as it's said sometimes. So basically, when it comes to rounding, you can round where you want to, unless it says otherwise. So sometimes a quiz or a test may ask you to round to a certain spot or homework problem, and then they want you to do that, and they want you to round correctly, of course. Otherwise, you can round where you want to, but you have to round correctly. I'm going to put another one here. Another couple. Okay, so which ones of these are good and which ones are not so good? Well, 3/8 is 1/6, right? Which is 0.1, and then 6 is forever. And then we multiply by 100%, so basically the decimal point moves over. So we get a number like this. And it just keeps on going. So if I want to round to the first decimal place here, I can, and this would be okay, right? If I'm going to round here, I can't leave it at 6 because this says move it up 1, so we're good here. Same thing here, right? If I want to round to the second decimal place here, right here, I look at that one, yep, it's bigger than 5, move that one up. What about this one? Not going to work, right? We can't allow that, because if you're going to round to that first decimal place, that needs to be a 7. So you can round where you want to here, just round correctly, right? What about this one, 17%? Well, just think, this person is rounding to the nearest percentage, so they're rounding right here. So they're okay, right? Because this 6 says move this one up 1 to 17%, so that's okay. Which means 16% wouldn't be okay because that's not rounding to the nearest percent. This one's a little tricky, but if you have the bar over the 6, that means this is an exact number. It means the 6 goes forever. So you're not really rounding here. So this is okay if you wanted to do this, because that 6 is repeating forever, so this would work. And then one of these is good, one's bad. Which one? This is okay, right? Basically, wherever we stop, we're going to need a 7, right? Unless, of course, in this case. So this is okay, but this is not okay. We can't put a 6 there. The last one is going to have to be a 7 if we round correctly. Okay, so it's a little rounding practice. And the coefficient of variation is just that little formula there. And then we just have one more thing here. So before we do Chebyshev's theorem, there's a little recall here. The spread or dispersion of data about the mean will be small if the standard deviation is small, like team 1, right? The spread of data about the mean was small with team 1 because they were all about the same height. It'll be large if the standard deviation is large, right, like team 2. So if you have a small standard deviation and you make a histogram of your data, there's just not going to be much variation. It could be something like this. Whereas if you have a larger standard deviation, you could have maybe data that are spread out all over the place. So small standard deviation here, there's not a lot of change here. But then this one would be more, just going to make this a little bit more symmetrical. So I have something like this. So these data points are kind of close together, small standard deviation. These are all over the place, larger standard deviation. Well, when we look at Chebyshev's theorem, this is there was a Russian mathematician who lived through pretty much throughout the 1800s, and he has his name all over the place. His name comes up in math, comes up in statistics, comes up in physics. He's did quite a bit of work. But for us in statistics, we're going to use Chebyshev's theorem, which gives us information about a set of numbers. It's actually a little bit surprising, the information we can get from Chebyshev's theorem. But Chebyshev's theorem would work on this data set or this data set, and in fact works on any data set. So we're going to see in Chapter 6 that if the data are distributed in a symmetrical bell-shaped fashion, we can accurately estimate the proportion of data that must lie within a certain number of standard deviations on either side of the mean. And we'll see this in Chapter 6 when we study the normal distribution, which is probably safe to say the most important distribution in all of statistics. So in Chapter 6, we'll see that if we have data that kind of like this pretty much fits, but if we have this normal, or we have a symmetrical bell-shaped fashion, we can use a normal distribution, which has been studied extensively, and infer a lot of things about the data. But if we have something that doesn't fit this category, it doesn't look like a nice symmetrical bell-shaped curve, then we can use Chebyshev's theorem. So the key to Chebyshev's theorem is it works with all data distributions. Kind of surprising when this happens, but the concept of data spread about the mean can be expressed generally for all data distributions, whether it's skewed left, skewed right, symmetric, or any shape at all. You could just make up a bunch of numbers right now in your head, and Chebyshev's theorem would apply to those numbers. So this is what it says. It says for any set of data, any set, meaning it works on this bell-shaped data too. But if you have data that fall into a bell-shaped curve, then you can get more precision using the normal distribution. So Chebyshev's will work on these, but it's better to use the normal distribution. But if you have data that are spread out all over or look weird like this, then the normal distribution won't work. So the nice thing about Chebyshev's theorem, it works on everything, right? So for any set of data, populations or sample, and for any constant k greater than 1, so k, this number k is going to be greater than 1, the proportion of data that must lie within k standard deviations on either side of the mean is at least 1 minus 1 over k squared. If you've never seen Chebyshev's theorem, this is going to seem a little confusing at first, but it'll just be patient. It'll all make sense in a few minutes here. So what this means is that for any set of data, any set of data at all, that's kind of a key to Chebyshev's, any set of data, at least 75% of the data fall within the interval from the mean minus 2 standard deviations to the mean plus 2 standard deviations. In other words, within 2 standard deviations of the mean. And that applies for samples or populations. So you could say or mu minus 2 sigma to mu plus 2 sigma. Right, it works for that too, for populations. So within 2 standard deviations of the mean, Chebyshev's theorem says at least 75% of all the data, at least 75% fall within 2 standard deviations of the mean. Then 88.9% of the data fall within 3 standard deviations of the mean, right? So the mean take away 3 standard deviations, 2, the mean plus 3 standard deviations. And finally, 93.8% of the data fall within 4 standard deviations of the mean. For us in this class, we're just going to see these numbers because they refer to k equals 1, 2, or 3. Or sorry, not 1, 2, or 3. 2, 3, or 4. 2, 3, or 4. And that's where this y comes in. If I plug in a 2 for k, and this is one thing, I'm going to write this in red because this messes us up a lot, so be careful with this. K is the number of standard deviations. Okay, we get confused on this all the time. So it's not the standard deviation, that would be little s or sigma, right? It's the number of standard deviations. So where these numbers come from is this. Let's use this one right here for the y. 88.9%. Well, this is basically saying, in this case, this means k equals 2. This is k equals 3. K equals 4. So if I use this formula up here and I plug in 2, 3, or 4, I'm going to get these percentages that you see. So this number here, 88.9%, it comes from letting k equal 3. If I let k equal 3, so 3 standard deviations, I plug in a 3 there. 1 minus 3 squared equals 1 minus 1/9. Well, just make this a little easier. A little arithmetic here. Isn't 1 the same as 9 over 9? 1, 9 over 9. So 1 minus 1 over 9 is the same as 9 over 9 minus 1 over 9. And I wrote it like this because then we've got a common denominator. So that's going to give us 8 over 9, which is, you put this in your calculator, 8 over 9 is going to be 0.8 repeating, which then if you write it in as a percent, it comes out to 88.9%. So these numbers are not magical. They come from plugging in values of k. If I plug in a 2 for k, wouldn't I get 1 minus 1 over 2 squared, or 1 minus 1/4? 1 minus 1/4 is 3/4, right? Or 75%. So as long as k is greater than 1, Chebyshev's theorem holds. But for us, we're just going to use k being 2, 3, or 4. So we'll see these numbers all the time with Chebyshev's theorem. We just have to realize that if they ask us to use 93.8%, we need to know that that means, okay, k equals 4. 88.9%, k equals 3. So there's a little note here. Chebyshev's theorem, it gives us the minimum percentage of data that will fall within the specified number of standard deviations of the mean. It's the minimum, so oftentimes it's going to be much more than that, but it's a guarantee theorem. It gives us the minimum amount. Okay, now that's still probably a little confusing if you've never seen Chebyshev's theorem before, but after these two examples, it'll make sense. Okay, so it's a little confusing at first, but let's try these two, and then I think you should be all set. So with this example, it says, suppose we have sample data. We know the mean is 18. You know the standard deviation is 3. So imagine this just being a pile of numbers. Maybe there's 7 numbers. Maybe there's 70 million numbers. We have no idea, but we do know this. We know the mean of the numbers is 18. We know the standard deviation is 3. And just with that little amount of information, we're going to be able to figure quite a bit out about how these data are distributed. So it says compute a 75% Chebyshev interval around the sample mean. So it's an interval of numbers, right? It's going to be an interval, so it'll be like from this number to that number, right? Interval. And it's going to be centered on the mean, so it's going to be centered at 18. It's going to be an interval around the sample mean. So what we have to look at is this. 75% Chebyshev interval, that means k equals what? And it's going to be 2. Now, we could get that from solving this, right, to 0.75. If we didn't know much, we could just solve this to get k equals 2. But for us, we're always going to see one of these 3 numbers, right? It's always going to be either 75%, 88.9%, or 93.8%. We just have to recognize, okay, this 75% is from, it means k equals 2, because if I put a 2 in here, I'll get 0.75. So what that means is this is what we do. Okay, k equals 2, so that means we are going to be within 2 standard deviations of the mean. So we're going to go just like this. We can go x bar minus 2s to x bar plus 2s. And the only difference for these problems is if this had said 88.9%, then I'd plug in a 3 here and a 3 here. If this said 93.8%, I'd plug in a 4 here and a 4 here. But it's 75%, so k equals 2, so I have a 2 here and a 2 here. And then we just do the math. X bar, they told us, is 18 minus 2s. Now here's where I have to be careful. S is the standard deviation, right? Which is 3. So I plug a 3 there. So I have 2 times 3 to 18 plus 2s, 2 times 3. Well, this is 18 minus 6 to 18 plus 6. This is 12 to 24. Okay, so we get this interval, and it's always going to be centered in the mean. The mean is always going to be right in the middle of this. 18 is right in the middle because they just subtracted one number and then added the same number, which is 6 in this case. But here's what it means. It means that no matter how many numbers are in here, we don't know. Maybe there's just a few, maybe there's millions. But we do know this. At least 75% of these numbers in this big pile are between 12 and 24. So here's the conclusion we can make. 75% of the data are from 12 to 24. 75% of the numbers in this pile, we have no idea how many there are, but 75% of them are between 12 and 24. 12 and 24. So it means 25% of the numbers here are less than 12 or more than 24. So that's what Chebyshev's theorem can tell us, which is kind of surprising, right? Because you can make up any set of numbers you want. Chebyshev's theorem will still work on that set of numbers. So, to get one more example, let's try this. This is one you should try yourself first and then come on back and see if we get the same thing. So it says, suppose we sample some Math 215 students in the JRCC Math Lab. We find that they studied an average of 32 minutes with a standard deviation of 6 minutes. Now, I know what you're thinking. You're like, 32 minutes? What? Rookies? Right? That's not long enough. I know. Maybe this is made up data. I know it would have been way more than 32 minutes. But just to get a little practice, They want us to use Chebyshev's theorem to find an interval center about the mean in which at least 88.9% of the data lie. 88.9. So here's where we need to know these numbers. 88.9 refers to k equals what? K equals 3, right? So we would go like this. We would say, okay, so k equals 3. So we're going to go x bar minus 3s to x bar plus 3s. So we're going to go x bar is 32, right? X bar is 32. Little s is 6. So we're going to go 32 minus 3 times 6 to 32 plus 3 times 6, which is 32 minus 18 to 32 plus 18, which means 14 to 50. So this is our interval, right? Centered about the mean. It always will be, by the way we do this. So 88.9% of the data lie within these numbers. So that means that at least, remember this is a minimum, at least, could be more, but at the minimum, 88.9% of the students studied between 14 and 50 minutes. So roughly 89% of them did, so it means 11% of the students studied less than this or more than this. So that is how you do Chebyshev's theorem. 3.2 is a little more challenging than 3.1, because standard deviation and some new things you may have not done before. So give it a try, and if you have any questions, let me know.